So number 8, an 1,800 kilogram car, that one there?
Yeah.
Okay, I can fix that. We can do that. I'll even cut and paste it. This is kind of a neat one because you guys are stupid in the way you drive. In a nice, loving teacher kind of a way, I mean, you're stupid. We need to talk about the physics. So it basically says, hey, what happens if you double your speed? What happens to your stopping distance? You okay with that? Well, they want a distance, I realize. I notice they've given me a mass, a speed, and a distance. I'm going to do this algebraically. I'm going to suggest to you that work equals force times distance. Is that okay, Ty? What's work the same as? What does work equal? Say it again. What's work the same as? But work is also the same as the change in kinetic energy plus the change in potential energy. So here's what I'm going to argue. Force times distance is that. Does this question mention or imply a hill at all? So is there a change in height at all? So is there a change in potential energy at all? Okay. So I get this. A half mv final squared minus a half mv initial squared. What's v final? I'm going to chuck the negative because all I'm interested in is the scalar result. The negative right there is just telling me we're losing energy. But what I'm going to do is I'm going to get the d by itself. Okay? If I get, how would I get the d by itself? In fact, I get this. Your stopping distance is equal to mvi squared all over 2f. I made the 1/2. I changed it into a 2 in the bottom. You okay with all that? Now, looking at this question, in the first situation, when you're going this fast, and in the second situation, has your mass changed? Has the force from the brakes changed? What has changed? The speed has doubled. But what do you notice? What do you notice about the, what is that sitting right there? So if you double it, you're actually going to get 4 times bigger an answer. If you're going 3 times faster, and this is for you drivers, it'll take you 9 times longer to stop. So one way to do this would be purely algebraically to say the answer is going to be 24 times 4. Doubling it actually because of the squared makes it 4 times more distance, and that's where the 128 comes from. Or you could actually have used numbers. So I don't know the force, but you could have found the force by using the, you could have solved for F by using distance is 32, VI is 24. You could have actually calculated the force and then got this by itself, made your new velocity 48, and you would have calculated the 128. But I couldn't resist a chance to do it generically and algebraically. Really, the message that I have for you is slow down. Oh, when it's raining or snowing, what happens to the braking force? Bigger, smaller, or stays the same? Waste, because it's friction, yes? So, hey, if it's raining, slow down, because what you don't realize is if this gets smaller and you're going twice as fast as normal, if this was the same, it would take you 4 times further. But if this is half as big, now it's going to take you 8 times further to stop than than you're used to. Slow down. It's nothing to do with your driving skill. It's physics. Can't argue. Is that okay? Yeah. It's a good question. Any others from the homework? Okay, I will take questions still later on as well, but I'm already deciding to put a few of the ones that kids have asked in the past on the test, because usually kids ask me questions about them. I think people maybe haven't done the homework yet, but okay, we're going to finish off lesson 2 today, and we're probably going to start a little bit of lesson 3 as well. So we started looking at the law of conservation of energy. I went on a rant about how hugely important this was. And I said there was 2 versions, one with heat, if they start talking about friction, one without heat, if they say no friction. So you all have this, I hope, yes? Lesson 2. Quinn, when do I use this? I said I use this when there is a change in height, a change in speed, and a yucky curvy path. I also will use this if the question uses scalar words. In other words, if the question doesn't say find the velocity, but it says find the speed, that's kind of my way of thinking, hey, maybe they're hinting use a scalar approach rather than a vector approach. Not always, but sometimes. Find it, Leonard? Yeah. Yeah, okay. It looked like you were turning the pages. And we left off right here. We did some cool demos. I showed you the chrome spheres that can burn paper. We talked about how with the super bouncers and things, you could get some nice chain reactions. Okay. Ready, Jordan? Ready, Jordan? Okay, good. Be quiet. Thank you. Sorry. A 3,000 Newton, okay, they gave me the weight in newtons. They gave me mg. The car is not 3,000 kilograms. The car is whatever times 9.8 equals 3,000, yes? At rest, at the top of an incline 3 meters high and 30 meters long is released and rolls down a hill. What is its speed at the bottom of the incline if the average friction force is 200 newtons? Ugh. Is there a change in height? Yeah. Is there a change in speed? Is there a yucky curvy path? Well, it's a ramp. There's definitely a slanty path. I think, Riley, I might want to try this with conservation of energy, but I'm going to dulp a little bit first. I'm going to dulp fairly small over here. It looks like they've told me this. They've given me a ramp, little car. They've told me the ramp is 3 meters high, and they've told me that, this distance here is 30 meters. Okay. Well. Colin, did this question mention heat? Did it mention friction? Then you know what? I think I'm going to gamble and say maybe they want me to do something with you know what? Because, I mean, if I cross it out later, that's fine. But I think I'm going to use this one. Are any of these zero? Is the initial kinetic energy zero? Yeah. At rest. Yay! Is the initial potential energy zero? No, you're not starting on the ground. Is my final kinetic energy zero? No. Is my final potential energy zero? Hey! So here's what I have. mgh initial equals a half mv final squared plus heat. Why do I think there's heat? Because they talked about friction, and I know heat creates friction. Okay. Do the m's cancel this time? No. Okay. What am I trying to get by itself? Let's minus the heat over. By the way, I could times everything by 2 to clear fractions, but there's only a single fraction of 1/2. I think I'll decimalize it and just divide it over. Yeah?
On your little drawing, why is the ramp 30 meters and not the bottom?
Because it says the ramp is 30 meters long. I phrased it that way very, 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 very carefully, intentionally, on purpose. You're going to see why in a second. You're anticipating where I'm going. Well played, I say. Well played. Because the problem right now, I mean, to get the V by itself, it's going to be divide by 0.5, divide by m square root, except I got that heat. Really, heat is the work done by friction. Hey, Tyler, work is what times what? I planted that earlier on purpose. I'm coming back to you on that. Okay. What work is what times what? Say it again. So I think the work done by friction would be the force of friction times the distance that friction was acting for in the same direction. And now you're seeing why I had to give you the ramp distance, because friction is acting, remember our free body diagrams, in the same direction as the ramp. I think the work done by friction is going to be the force of friction times 3, no, times the base, no, I could figure out the base with Pythagoras, times the slanty part in the same direction that friction is acting. Uh, 200 times 30, 6,000, I think, if I do the math in my head. That's how many joules of energy were lost to heat, or were converted to heat. So, I'm going to get this. mg 3,000. I don't know the mass, but they gave me mg because they gave me the mass in newtons. H 3 minus heat 6,000. And then to get the V by itself, divide by 0.5. Oh, I am going to need the mass after all. Well, they told me the car had a weight of 3,000 newtons. I guess the mass is 306.1. 2, 2, 4. You know what? I'm going to use my answer button, Mac. So I'm going to go 306.1. Now that equals VF squared. Jordan, how to get rid of a squared? Do you say square root? I think you'd be right. Square root looks correct. Is that a fairly yucky square root, Jordan? You know what? I'm going to type the whole thing, hit equals, and then square root answer button. I'm going to go like this. Bracket 3,000, there's my mgh, minus 6,000. I probably could have done that in my head because it's 9,000. Take away 6,000 is probably 3,000. Well, whatever. Divided by bracket 0.5 times answer button. Oh, that's a fluke. Square root answer. 4.43 meters per second. That trick there, Quinn, of if I tell you the force of friction and how long it acted for, you can figure out the heat. I like that, I like that, I like that, I like it. Or if I tell you the heat, you could then, and you know how long the ramp is, you could actually figure out what the average force of friction was. You could find the, in other words, if you knew the work done by friction and the distance, you could find the force of friction. Heck, you could even find mu. What's mu? I don't know. What's mu with you? You could find mu. There's another force that was always showing up on ramps. Remember the normal force? So I wrote here, technical comment on ramps. The normal force does no work because the normal force is always perpendicular to the direction of motion. The angle is 90 degrees, and we found that when we did that cos theta equation, cos of 90 was 0, and so the normal force does no work. I can ignore it. So if a ramp is frictionless, or if it's really, really well greased so that we get mu as low as possible, the energy is really conserved. Nothing goes into heat. That's why we grease down roller coasters. The same argument also applies to rope swings. Tarzan. Tarzan has a mass of 85 kilograms. And he runs at 6 meters per second. He grabs onto a vine and he swings up until he stops. A says, write a work energy equation. B says, how high can he swing? So if you look up, we're talking about this. Here's the vine. Tarzan's going to come running, 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 running. He's going to grab the vine and swing up. Addie, is there a change in height? Is there going to be a change in speed? Is it a yucky, curvy path? I think this might be a job for conservation of energy. So when it says write a work energy equation for part A, I think I'm going to go like this. Addie, does this question talk about or hint about friction or heat or anything like that? So I'm not going to go plus heat. Are any of these 0? No, we want final to be here, because how high can you swing? Is that okay? So is PE final 0? No. Which one?
PE initial and K.
PEI, Prince Edward Island gets hosed again.
And KE.
Oh, and at the top of the swing for a split second? This, by the way, trying to analyze this curvy path with vectors, Jake, would be ugly. Ugly, ugly. But you're going to notice with a scalar approach, I get a beautiful equation. Oh, and not only that, what else do you notice? It turns out the height that Tarzan swings to would be the same as the height that Tantor the elephant swings to, assuming the vine could hold the mass and not snap. But if the vine could hold the mass, if Tantor the elephant ran at 6 meters per second and swung up. And there's another nice thing about the fact that this is a scalar. I realize, don't write this down. So here's the vine. Here's Tarzan. The ground is probably here. You know what? I can put the height of 0 wherever I want. I'm going to put the height of 0 right there, because this is a scalar approach and it doesn't care about my path. All it cares about is where you started and where you ended. So even though technically we're not on the ground, that's why I could cross that out. I could say, I'll let that be the 0 energy point. And I'll cross that out. How would I get the h by itself, Addie? Nice. So I get this. The final height is going to be V initial squared all over 2G. I made the 1/2 into a 2 at the bottom because to me that looks prettier. It's going to be 6 squared divided by 2 times 9.8. And again, just to remind ourselves, why am I not putting negative 9.8 in a scalar? Don't care about direction. 1.84 meters? Okay. So rope swings are great applications of potential the law of conservation of energy, G. They really work great. Video, potential to kinetic energy. Okay, put your pencils down, look up. So, roller coasters. I love roller coasters. I'm going to tell you right now, I guarantee on your test there's going to be an amusement park ride or 2 or 10. At least one, though. It's going to be a roller coaster. I'm nuts about roller coasters. So here's a roller coaster. Well, you know, I couldn't get the wheels to go, so instead I made it a frictionless ramp. But you know what? That's the same as wheels rolling anyways, so humor me. If this ramp is frictionless, it says write a work energy equation and find a speed of the 1,000 kilogram roller coaster at the bottom of the ramp. And then B says if the speed at the bottom of the ramp is 12 meters per second, write a work energy equation and find the energy loss due to friction. I'm guessing in part A we'll get an answer bigger than 12. And then we'll find out when we did the experiment, oh, we got 12, we must have lost something to friction. Riley, is there a change in height? Is there a change in speed? Is there a yucky, curvy path? This is a job for conservation of energy. G. So I'm going to start doing part A, I think, right here, just so I can get it all on the same screen. And I'm going to go K, E initial plus P, E initial equals K, E final plus P, E final. Are any of these 0? Are we starting out at rest? Look at the picture. Are we starting out at rest? No! Are we starting out on the ground? Are we ending up at rest? Are we ending up on the ground? Okay. By the way, this explains, and you've noticed this, where is it fastest on a roller coaster? At the bottom. Why? Because that's when the most potential energy has been turned into what type of energy, boys and girls? Kinetic, the energy of motion. A more interesting question is, where is the best place to sit in a roller coaster if you want to experience the biggest acceleration and g-forces? Front, middle, or bottom? I actually posted this on a physics teacher's forum about 10 years ago, and it led to some great discussions. And our consensus is middle. Why? Because that's where the center of mass is. So that's when you're going to experience the biggest changes in velocity, the biggest accelerations. That seems to be the consensus, but I'll happily discuss this with you another time. The front is better for the visual psychological aspect because there's nothing in front of you. The back, sorry, we'll differ and argue later, but not right now. I'll come back to it at the end. A half mv initial squared plus mgh initial equals a half mv final squared. Jose, have you been on a roller coaster? Did they make you step on a scale before you got on the roller coaster? You know why? Well, that's kind of cool. What am I trying to find here? You know what? I'm going to do that trick because I got halves all over the place. I'm going to do the times by 2, times by 2, times by 2, because that'll cancel, and that'll cancel. In fact, what I'll get is VI squared plus 2GH equals VF squared. I showed you guys last class. That's really VF squared equals VI squared plus 2AD in disguise. Oh, how'd I get rid of a squared? Square root. So I'm going to get two squared plus 2 times 9.8 times 10. In theory, how fast are we going at the bottom? Square root of 200? I think I could do that in my head. Isn't it going to be 14.1? Yeah. I know the square root of 100 is 10. I know the square root of 2 is 1.4. So 10 times 1.4. 14 point, yeah. That would be the in theory in our magic. By the way, you'll notice I gave you the distance of the track. Did I need to use it? No, I didn't bother. Totally just to throw you off. I gave you the mass. Did I need to use it? Didn't bother. Totally throw you off. But suppose we ran the experiment and all we found was the speed of 12. Okay. How much heat did we lose to friction? B. Is there a change in height? Is there a change in speed? Is there a yucky curvy path? This is again a job for conservation of energy. But this time, Colin, my friend, they're talking about heat. I can still do that. What am I trying to find this time? Heat. How would I get the heat by itself? I don't know what happens here, Tyler, but time and time again, and I haven't figured out why, for some reason, kids divide by KEF. I kid you not. It happens every year on my test. If I have 60 kids writing it, 4 or 5 will divide. Don't, please. It is minus. So if I hear you correctly, it's going to be, I'm going to write the heat first now, if that's okay, Ty. It's going to be KE initial plus PE initial minus KE final. Heat is going to be a half mv initial squared plus mgh initial minus a half mv final squared. Okay with that, Mac? Does the mass cancel this time? Isn't there a mass in everything? Ah, no, what isn't there a mass in? Okay, so I've lied to you. Jose, have you been on a roller coaster? Did you step on a scale before you went? But is there friction on a roller coaster in real life? So does the mass cancel in real life? But wait a minute. How can we get friction as low as possible? What do we do with those roller coasters and those wheels? We grease them. We can't change, because friction is mu times the normal force. We can't change the normal force. We can sure change mu, the coefficient of friction. So what we do, Ty, is we get the friction force down so low that really the mass is negligible. And that's why an empty roller coaster will make it through the system. That's why a full roller coaster will make it through the system. But it is true. How many of you have been on California Screaming, for example, at Disneyland? You may notice near the very, very end, they slow you down a tiny bit. There's some software that does take into account the fact that, okay, mass doesn't quite cancel. But in our magic physics world, it does. Is that okay? Well, let's plug and chug. I'll do heat in red. 0.5, I think I said the mass with 1,000, yes? Did I say the mass with 1,000?
Yeah.
Yeah. 2 squared plus 1,000 times 9.8 times, I forgot H, 10? Wow, I picked nice numbers here. Minus 0.5 times 1,000 times 12. Don't forget the squared. Other most common mistake, kids forget the squareds. 0.5 times 1,000 times 2 squared plus 1,000 times 9.8 times 10 minus 0.5 times 1,000 times 12 squared. 28,000 joules? Pardon me? I'd have to crunch some numbers to see whether, because the mass is in there, I'd have to see whether that's a really big difference. Well, I mean, it's 12 meters per second versus 14.1 meters per second. You could calculate the percentage difference in speed if you wanted to, but it's not that significant. You know what else I can do? We can add a part C. Find the average force of friction. How? What did we just find? The work done by friction is another way to think about it. So I think what I can say is 28,000 equals the force of friction times distance. Did they tell me how long the ramp is? But Mr. Duke, it's a scalar, I don't care. Although that's why I said average force of friction, because I suspect if your ramp changes its angle, the friction, because the normal force would change, the friction force would change. This will give us the average force of friction. How would I get the friction by itself? So the average force of friction is going to be 28,000. What was, which distance? 17 point, the distance in the same direction that friction acted, which would be the length of the ramp. You see why I phrased it that way now? Yes? 17.5, is that right? Holy smokes, that's a fluke that it worked out evenly. 1,600 newtons? Hey, you know what else I could find? I could say, find the average or could I? What's mu? I don't know. What's mu with you? Friction is what times what? The problem here is because the ramp is changing, the normal force, which is perpendicular, would always be changing because theta would always be changing. Although I guess I can get the average coefficient of friction. What would, well, I mean, really, if I wanted to find an average normal force, it would be this. 10 by 17. Just put it face down on the right block and then come join us. Could I find theta if I treated this like a triangular ramp instead of a curvy ramp? Which trig function would give me the angle? Sorry? Sine? So, sine theta, we're picking up from where we left off yesterday, equals opposite. How big is theta? It's going to be inverse sine of 10 divided by 70. We haven't found an angle for a while, but right, that's how we did it. If I wanted to average this out, the average angle is 34.8 degrees. I know it goes steeper, I know it goes shallower, but that's the average. Okay, let's go back down to here. Right? I don't know the normal force. Oh, but look. I have a ramp. Who remembers what was the normal force equivalent to on a ramp? And please don't say mg, because it wasn't. Of course it was. So you ready? Mu is going to be friction divided by mg perpendicular, which is going to be friction divided by mg cosine of the angle. 1600 divided by 1000 times 9.8. And Tice, this is going to be a better answer to your, because if we get a low mu, then we'll realize we didn't lose much at all. If we get a big mu, we'll say we better add more grease, right? Cos, what did I say the angle was? I'm going to use my answer button anyways. 34.8. What's mu? I don't know. What's mu with you? That's not great. Probably I could grease it down better. 0.20 or 0.199. Let's go with that. Let's go to 3 sig figs. 0.199. So all of this stuff, if we tried, Jordan, using only a vector approach, it'd be ugly. But you'll notice we can tackle things with a scalar approach. Bring some vectors in later on if we need to. When do I use the law of conservation of energy? Change in height, change in speed, yucky curvy path. Roller coasters. Are you asking me, will there possibly be a question where I say find the heat and then say do something with the heat? Yes. I don't think I'd give you one quite like this where I didn't give you theta. I would have no problem giving you a straight ramp question without a curvy path, where I gave you theta and I gave you the length of the ramp. You know what? I'd have no problem if I gave you theta, gave you the base, gave you the height, and made you do Pythagoras to find the length of the ramp. That's fair game as well. Okay. What's your homework? So we can add number 1 and number 2. Can add number 6, number 7. Number 7, before you turn the page, number 7 is asking you to find how much work was done by going force times distance. You can find the force by going winner minus loser. The force is tension. And then it's also asking you to find how much work was done by going change in potential plus change in kinetic. Should get the same answer both ways. That's why, yes, yay. Okay. Nine, I skipped 8. 10. All right. Lesson 3. Power and efficiency. Power. The word power is used in a variety of ways in everyday language, but in physics it has a specific meaning. Power is the rate at which work is done. It's how fast you're doing the work. It's the rate at which energy is transformed from one form to another. Power is tiredness. If you're getting tired doing something, it's not because you're doing work, it's because you're doing the work quickly. You're expending the energy quicker than your body can replace the energy. When you're talking, when you say, oh, I'm so tired, really it's because you were generating a lot of power. It's a scalar, and it's defined as the work divided by the time. What are its units? Well, I guess it's a joule per second, work divided by time, but this is such a fundamental unit, we've given it a name. Power is measured in what? Yes. Symbol, capital W. Power is measured in watts. Oh, you just got the joke now? Power is measured in watt?
No.
What, the W for work and W for watts?
Yeah, watts.
Well, that's because we got 26 letters of the alphabet. If we were smarter, we would have put like 50 or 60 letters in our alphabet. Okay? You'll know because it's going to appear after the number as a unit, right? I mean, the same way N is Newton and N is north, we've handled that just fine. Mass is meters, mass is mass. We've handled that just, you'll handle it fine. A girl runs up a flight of stairs 3.32 meters high in 2.6 seconds. What's her power output in watts? Power equals work over time. Definitely the time is 2.6. When you climb upstairs, what type of work are you doing? You're really gaining potential energy. Hey, I have an equation for that. It's going to be 60 times 9.8 times 3.32 divided by 2.6. How many watts of power has she generated? $751? Yes? Watts. What if she ran the stairs faster? What would happen to the time value? What would happen to the power that she generated? What would happen to her fatigue? More tired. This is why I'm saying power is what really causes tiredness. Or, what if she was heavier? What would happen to the power required for her to climb the stairs? If her mass was bigger, what would happen to the power required? Okay, this is why heavier people get tired so much faster doing the same task. It's not like they're lazy, it's actually, it's physics. It's costing more energy per second for them to do the task. If 1 horsepower equals 750 watts, what's her power output in horsepower? She outputted almost exactly 1 horsepower. What's a horsepower? It's the imperial unit of power. So the horsepower was originally invented by James Watt, for whom the unit of power is named. I think I said this in Physics 11, but I'll say it again. He's overrated. I'm disappointed that they named a unit after James Watt. He really didn't advance science very much. What he did was he improved the steam engine, and he was a great marketer. Because he had improved these steam engines and he was trying to sell them to factories and farmers. And the factories and the farmers say, yeah, we have no idea what it is we can do with that. And so this is where he was a great marketer. He invented a unit, the horsepower. So when he said to a farmer, this motor has 3 horsepower, what does the farmer think? This motor can do the same amount of work as? He'd removed the mystery from the steam engine, and now they could wrap their brain around it. Now, by the way, it doesn't mean it can do the work of 3 horses. It's a made-up unit, but it was a great marketing tool. He sold a bunch of them. Oh, a 5 horsepower motor will do the work of 5 horses. Okay, I know how much I spend on feed. I know how much the 5 horses would cost me. I can figure out how much I'm willing to pay for your engine.
What is the power output of a horse? Is that like?
And see, this is the, by the way, this is the beauty of how good a marketing strategy it was. We still measure engines in horsepower, despite the fact that we haven't used horses to power things for about 100 years, and nobody now knows what the power output of a horse is, but we'll still try and tell you that that Corvette has the power output of 300 horses. Whatever the heck that means, I don't know. Okay? In your homework, there's going to be 1 or 2 questions where either it gives you something in horsepower or asks you to convert it to horsepower, and you can use 1 horsepower equals 750 watts as your conversion factor. I'm not going to ask you horsepower on a test. But it is true, motors are measured in horsepower, so I will capitulate because I do want to show you where stuff is applied. We have a 5 horsepower motor. It's printed on the side. How long would it take for this 5 horsepower motor to lift a 500 kilogram safe up to a window 30 meters above the ground? Okay. What's this question asking me to find? I'm deficking because we're in new material here. What have they given me? Well, looks like they've given me power, but they've told me 5 horsepower, which I guess I'm going to multiply by 750. 5 times 750, 3,750 watts. What else? Somebody said they gave me a distance. I agree. What else? They gave me a mass. Well, first thing I would say is I'm looking for an equation that has power and time in it. It's our new equation of the day. By the way, this equation, P equals W over T, is on your formula sheet. It's always a change in, but I'm too lazy to write the delta because by definition time is going to be a change in. Yeah. How would I get the T by itself? Oh, is this technically 1 fraction equals 1 fraction? Stuff moves diagonally. Are you kidding me, Mr. Dewick? Time is going to be the work divided by the power, where the power is 3,750. What if we said the work done when you're lifting something is defined as, hey, that's the change in potential energy. That's, oh, we have an equation for, yep. $500 times 9.8 times 30. How long will it take to lift this safe? $39.2 seconds. It's impossible to do it any faster than that. In fact, even this is wrong. This is assuming this motor is 100% efficient. This is assuming that all of the energy goes into lifting. I imagine you could hear this motor. You'd lose some energy to sound. If this was a gasoline motor, it would be giving off some heat, a lot of heat. If it was an electric motor, it'd be giving off some heat. You'd be losing some energy. So this is our theoretical minimum time. It's probably going to take longer. Power. Yeah.
How can you calculate the energy loss to other things, like not just heat?
You can calculate it directly. We don't have the skill for that, and we won't. What you can do is you can calculate it indirectly by saying, well, how long should it have taken in theory? How long did it take in this example? Or how fast should it have been going at the bottom of the roller coaster in theory? With my radar gun, I'll measure how fast it's actually going. I guess the rest went into, but I'm lumping it all into heat when really some of it would have probably gone into air resistance because you're giving kinetic energy to air molecules. I've stood near roller coasters or trucks or vehicles and you get a big breeze as they come by. That must mean they pass some of their energy onto the air molecules. There's always sound. So there are ways, but like air resistance again is a bear. I've never taken a course on air resistance. It's part of fluid dynamics. My kids who have gotten physics degrees have told me that's always been the toughest course they've taken, fluid dynamics. It's calculus plus calculus equals more calculus plus more calculus, with a little helping of some sprinkling of calculus thrown in. Okay. When you know what? I've done first and second year calc, so I'm okay. But if you truly wrap your brain around calculus, suddenly the universe just makes way more sense. It's not a coincidence that shortly after 1687, when Isaac Newton published his Principia and released calculus to the world, the Industrial Revolution happened within 30 years because all these engineers were now oh, I can solve stuff instead of building it, finding it didn't work, and having to start from scratch. I can plan things out ahead of time. Meanwhile, power, I want to give you another definition of power. So power is measured in, power equals work over time. But Tyler, work equals what times what? See it right there? All of you, take your pencil out right now and circle that. What is distance measured in? What is time measured in? What is that I've circled if it's a meters on top and a seconds on the bottom, actually? What is meters per second? Someone said velocity. I got to be fussy. We're in scalar land. Turns out another way to calculate an object's power is force times average speed or velocity. When do you use that, Mr. Dewick? If they say find the power, but they haven't told me a time, but they've given me a force and a speed. That's not on your formula sheet, but did I show you, Ty? It's a fairly easy derivation. Okay. We're going to come back to efficiency. I'd like you to go to example 4. What is example 4 asking me to find? So I'm going to start out by going power equals work over time. Tyler, what's work? Force times distance over time. Hey, did they tell me a time in this question? No? Look, 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 look. Did they give me a speed in this question? So now you know when you use that second mini version, it's a question like this. Which force, by the way, well, if we're going at a constant speed, it means the forces are balanced. The applied force is what's doing the work. Which force is it exactly balanced with if we visualize the free body diagram? Friction. So I'm going to write power work equals the force of friction times speed. I'm not saying friction is what's doing the work. What I am saying is, you know, the force that's doing the work has got to be the same size, because why? Constant speed. Otherwise, it would be accelerating. See how we're putting, wow, almost the whole year's worth of stuff together in one nice little question there. Hey, friction is what times what? Mu times the normal force times V. I don't know the normal force. You know what? Here's our free body diagram. Right? All the top and bottom arrows will be the same length because we're not sinking into the ground or flying in the air. The left and right arrows, I drew them longer, but they'd be the same length as each other as well because it's a constant speed. I don't know the normal force. Oh, but look, 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 look. And did they give me mu? There you go. 0.25 times m times 9.8 times 2. How many watts of power are we outputting if we're pushing this? $490? Power is measured in watt? Now, how much work are we doing on this object? The net work, 0. Why? Are we going at a constant speed? So is this object gaining any kinetic energy? Is there a change in kinetic energy? Does this question mention a hill? Is there a change in height? So this is where that definition, don't write this down, that work is change in kinetic plus change in potential. Constant speed means no change in kinetic. Constant, you know what? You're not doing any net work. You're getting tired, but where is all the energy being transferred to? Heat in the floor. Friction. Okay. A girl pushes a 300 Newton box along the floor for a distance of 4 meters. Coefficient of friction is 0.33. She then lifts the box straight up 1.2 meters. What's the minimum amount of work she has done? And then we're going to do 6 next class, 7 next class, 8 efficiency. Yeah, we can get it all done. You know, you got room, let's do a little free body diagram. What are the forces acting on this box while she's pushing it? Get the obvious one. Get the obvious one. Thank you. Is it sinking into the floor? Is it flying into the air? So we have a normal force. Here's the girl pushing. Now, underline the word minimum. I added that for a reason, Colin. Minimum, let's assume the box isn't speeding up or slowing down. If it was speeding up, she'd be doing more. So I'm going to draw my friction arrow the same length as my applied. Seems to me she does 2 types of work here. She does work while pushing. She does work while lifting. And you know what? The total, I can add them up even though one's horizontal and one's vertical. Why can I add them up? I'm looking for a word that begins with the letter S and rhymes with, yeah, scalar. Scalar. Okay. Push. Work equals F applied times distance. I don't know F applied. Oh, but look, 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 look. I know another force the same size as F applied. Which one? Friction is what times what? I don't know the normal force. Oh, but look, 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 look. I know another force the same size. Boy, you're cluing in. These free body diagrams are kind of handy if you take the time to draw them. Aren't they? Just saying. So you're going to get mu mg times d. Yes? How much work to push? Minimum, constant speed, 0.33. Mr. Duick, they didn't give us the mass. No, I gave you it in newtons. I gave you mg, 300. That's mass times 9.8. D4. 1,200 times 0.33. Should be like really close to 400, I think. 396. Newtons, Mr. Duick? No, it's work, joules. That's how much energy she expends sliding the box for 4 meters. And again, that's the minimum because, Justin, if she was speeding it up, she'd be doing more. That's why I said what's the minimum amount of work she's done. She comes to a stop. Now she's going to lift it. Did I say lift? So now let's do the work done. Oh, how do I calculate the work done in lifting an object in, dare I say, changing its potential energy? MGH. Mr. Duick, they didn't give me the mass. No, but I did give you mg. 300 times h, 1.2. Hey, I can do that in my head. 300 times 1.2 is 300 times 1.2 is 360 joules. What's the total amount of work she did? I think I can do that in my head too. It's going to be really it's going to be 400 plus 360. It's going to be 760 take away 4. 754? 56, sorry, 756. Again, to try and do that with a scalar-based approach, Sorry, with a vector-based, I said scalar-based. With a vector-based approach, because of the changes in direction, ugh. With a scalar approach, yay! So your homework is the stuff I added last day, but questions you can already do from today, from this homework as well. You can handle number 1, you can handle number 2 if you want to get a head start. Otherwise, this is going to be homework next class. Next class, you won't be getting any new homework. You'll be getting a take-home quiz. That's Monday. 1, 2, 3, 4. Cross out 5. It's cool, you can find the angle, but I'm not going to worry about it. 1, 2, 3, 4 is good. We've been talking about conservation of energy and energy transformations.